Okay. Hi guys, I'm Pietro. I'm from the WSEC group, which is the system and security groups from the Vrije Universiteit of Amsterdam. And this work was my master thesis, which I did in cooperation with Cristiano, Herbert, and Cave, which are the three main professors of the group. So let's start with understanding what's glitch. So glitch is the first rammer exploit from JavaScript on mobile. So before this study, there was no proof of a JavaScript exploit using rammer on mobile. And it's not only the first one, but it's also the fastest JavaScript-based rammer exploit so far. But what's the main contribution of this work is the fact that it's the first GPU-accelerated bit flip. So we triggered bit flips not using the CPU, but the GPU. Now, to understand a bit the context we're working on, I'm going to go through the chronicles of glitch. So just give a bit of a contextual background and why we did this. So this is a bit of a timeline, and that little guy there is me. And it was mid-2016, I was looking for a master thesis, and I met Cristiano, now my advisor, who was talking about Rohammer, DRAM, and bit flips at a conference. And that time, I didn't know anything about this, so I was kind of confused. I didn't know what was going on. So let me explain to you a bit how this works and how DRAM works and what is Rohammer. So this is how you can look at DRAM, which is basically a grid of a lot of cells. And these cells contain capacitors. And capacitors, if you have any background in electronics, they don't keep the charges forever, so they leak charge over time. And as a consequence, they need to be refreshed to keep the data. Otherwise, you will lose your data that you store in DRAM. And that's also why it's called DRAM, Dynamic Random Access Memory. And the way a DRAM read works is if you have data, for instance, in row 2 that you want to read, what you need to do is you get that data, so you activate the row, which means that you bring it to the row buffer. And the row buffer is this one down there, which is basically a cache for DRAM. And once the data is there, the data gets removed from the row. So the way capacitor works is to get the content of the capacitor, you need to leak the charge to something else to read what was there. So if it's charged, it might be a 1 or a 0, depending on the encoding. And once it's in the row buffer, you can read the data from there. But then you need to send it back to the row. So you need to pre-charge the row or restore the data to have it still in memory, otherwise you lose it. Now, what researchers discover is that if you perform a specific access pattern, so usually what they do is they choose 2 aggressor rows with a victim row in the middle. If you access the aggressor rows fast enough, you might have charges in the victim row that start leaking. And at one point, you can trigger a bit flip, so you can change the data from a 1 to 0 or 0 to 1, again, depending on the encoding. And this is quite important because it means that you can compromise the integrity of data in DRAM without actually accessing it. And the crazy thing of all this is that once you get a bit flip, you may think, okay, that's a random error. But the thing is, once you get a bit flip on a specific cell, that bit flip is usually reproducible, so you can reuse it later on to compromise sensitive data. So back to the timeline, I started studying a bit the history of this bug, and it turns out it was quite recent. So the first proof was in 2014. They were showing that it was possible to flip bits in memory without accessing them. And then just 1 year later, Google Project Zero thought, okay, you can actually exploit this. It's not just this reliability issue. We can actually build a root exploit with this. And the same year, people showed that it was possible to trigger these bit flips from JavaScript. And at the same time, also in our group, some people were working on that and also working on breaking the cloud, so compromising virtual machines in the cloud. So I did a bit of recap, and I thought, okay, there is a root exploit, 2 JavaScript exploit, 1 on the cloud. So the next step is clearly, can you trigger these bit flips on your mobile? And turns out that somebody else already thought about it. So Victor, another guy from our group, but at that time it was not yet my group, so I was not aware of this, was working on this exploit that could root Android phones using bit flips. So I thought, okay, still I don't have a topic for my thesis. But then it turns out that while Victor was bragging on Twitter about his work, he was saying that he would think that it could be possible to trigger this also from a browser. And clearly, that's not that easy. So the Grudge, which is quite famous in the community, said, well, I would love to see that happen, like calling me out on his bullshit. So challenge accepted. There was a cool project to work on. And I started looking into what you need to build this kind of attacks. And when you think about attacks, usually you think about the primitives that you need to build the attack. And in the case of rammer attacks, you have two main primitives. The first one is fast cache eviction. So what are the caches? Well, usually when you read data from DRAM, you don't want to always access it from DRAM because that's very slow. So CPUs usually include another layer of smaller memory, which are called caches. And these ones are just used to hide the latency of these memory accesses. So what happens usually is that you go to the cache, check if the data is there. If it's not there, you get to DRAM, and then you bring it to the cache so that you can reuse it later on. And the next time, though, even if you want to access DRAM, the data is going to be in the cache. So you're going to get it from the cache. So if you want to touch the same memory location, the next time you're not going to do it because it's in cache. So the solution to this are two. The first one natively is to use the CL-flash instruction, which basically remove the data from the cache, so it just flashes the cache line. So it means that it gets the cache line and just send it back to the memory, so the next time you can get it back from the memory. And this is a really good solution. But on JavaScript, you don't have this luxury, so you need to do something different, which is called cache eviction. And the way this works is that you need to touch a bunch of random pages. So you just touch different data, until at one point this data is going to be removed, and then you can access it again to trigger the bit flips again. The second primitive that you need is contiguous memory. So as we said, we usually need 3 adjacent rows. So you want to have the 2 aggressor rows and the victim row in the middle. And this is usually supported by using transparent huge pages, which are basically pages of 2 megabytes. So usually in virtual memory, you allocate pages of 4 kilobytes. But with 2 megabytes pages, you can span over multiple rows in memory. Now, the mapping, it's not linear, so you don't just follow the addresses that you have in memory into DRAM cells, but it's a simplification that works pretty well now. Now, when you bring all this to mobile platforms, so on ARM, it turns out that CL-flash, it's a privileged instruction, so you cannot use it as a user-specific application. And eviction sets also don't work because the CPU caches are too large and implement a random replacement policy. And this means that, for instance, if you want to trigger your rammer bit flip, what you would do is you touch the first row, and then the content goes to the cache, the second row, and the content goes to the cache. And then you will start evicting. So you touch the one page, another one, and you keep on doing it. And sometimes you may actually evict something that you use for eviction, so that's not really efficient. Until at one point, you're going to remove the content from the cache, and you can access it again for your bit flips. But this doesn't work because it takes forever since the cache is large, and as a consequence, this is not an option on ARM. And about contiguous memory, transparent huge pages also are not available. So I was wondering how Victor did it, so I asked him, so how did you do it on ARM? And he answered Ion, and that for me it was, okay, what are you talking about? And Ion apparently is an API provided by the Android kernel that provides you with DMA memory. And DMA stands for direct memory access, so it's memory that usually is used by peripherals. And peripherals, for instance, if you have PCI peripherals, they might not have a memory management unit, which is the one that translates virtual to physical addresses, so you need the contiguous memory. And also, these peripherals usually don't want to deal with cache coherency, so the memory is also on cache for the CPU. So lucky Victor, but not lucky me, because it means that I don't have access to this memory from JavaScript. So I thought, well, we're screwed. We cannot do much now. And then I started thinking a bit, and I thought, well, what if we change the attack vector? And what do we mean by that? Basically, when you consider this kind of attacks, you have your JavaScript code running in the browser, which then runs on the CPU, and then use it to trigger the bit flips on DRAM. But it turns out that in modern systems, you don't have only a CPU, but you have a system on chip that contains a CPU, GPU, digital signal processor, and whatnot. And the CPU is not the only one available from the web, so you can run your code on JavaScript, in JavaScript on the CPU. But as you maybe have guessed from the title of this talk, you can also use WebGL on the GPU, so you can run code on the GPU from the web. So back to our primitives. Now we need to figure out how to get these two from the GPU. And also we need to figure out how to get DRAM access, first of all, from the GPU. So to understand how we get DRAM access, we first need to understand how the GPU works. So let's have a bit of introduction of how this works. So the GPU has the purpose of aiding the rendering pipeline, which consists in mainly 4 stages. At the beginning, you have the CPU providing with inputs the GPU, and these inputs is vertices. And then these vertices are sent to the GPU to run a bunch of computations on them. And the first one is some geometrical computations that are performed by the vertex shader. So these computations are usually rotations or translations, and then you get the output, the modified vertices. At the output of the vertex shader, you will get a polygon, which basically is the edges that connect these different vertices. And the polygon contains all the pixels inside these edges. And the pixels are, it's not exactly a pixel, they're actually called fragments, and the fragments are the one that get sent then to the fragment shader. So the fragment shader has the purpose of coloring these pixels one by one. Now, usually, you don't want to just draw a red triangle. That would be kind of useless. So you want to use textures to do to make fancier renderings. And therefore, the GPU needs to accept these textures as an external input. And then, in this case, you will get your wooden texture to color your wooden triangle. And now the output is going to be your wooden triangle on the screen of your smartphone, so on the frame buffer. Now, how does this work on the GPU architecture? So this is an idea of how the GPU looks like. And you have these units, which are the stream processors, which are basically the main cores of the GPU. And you usually have multiple of them to parallelize as much as possible your computations. And what they do is they start by querying the vertices from DRAM to run the vertex shader. So you get the polygons at the end of the vertex shader inside your stream processors. And then what it does is query these other units, which are the texture processors, to get the texture from memory and fill in the fragments with the associated pixel of the texture. And at the end, you will get the content in the frame buffer. Now, this gives you 3 possibilities to get DRAM access. These are the 3, so the vertices, and the texture, and the frame buffer, as you can understand. And it turns out that reading the texture is the most predictable one. So it's the one we chose. And the way this works is you can just write a program. So this is an example of a fragment shader, where you use this instruction, the texture2D instruction, to get the content from a texture at specific coordinates. And the way you can see this is basically saying you have an array, which is your texture of raw data, and you access at index coordinate that content. Now, again, the mapping is not super straightforward, but once you know the function that is used for the mapping between the raw data and the actual pixels, it's easy to touch specific locations in memory. So we have DRAM access. What about the caches? Well, we didn't mention them, but there are also here 2 levels of caches. So L1 and L2 are 2 levels of caches. And they do the same thing as for the CPU. So let's say, again, you want to run this code. You would get the content for the variable A from the texture. So the texture processor is going to query the memory and then bring the content to L1. And the next time, you're going to get it directly from there, so you don't touch memory anymore. And so what's the advantage of using the GPU? So if you still have the caches, what's the point of using it at all? It turns out that these caches were not documented at all, so we had to reverse engineer them ourselves. And they're quite different from CPU caches. So the difference is that the caches are very small, and they implement a deterministic replacement policy. And this means that once you want to trigger your bit flips, what you need to do is just touch the first row, so row n-1, and then bring the content to the cache. Same for row n+1. And then you start evicting. But the eviction here is deterministic, so you know how many accesses you need to perform. And at the same time, you know that every time you do it, it's going to be the same. So you know that for sure, once you access enough objects, which can be 16 or 8, or depends on the GPU, you will remove the content, and you can trigger your bit flips. So yay, it's fast enough for bit flips. We can use it. And so the next step is trying to figure out how to get contiguous memory. And to do this, we first need to understand how the memory gets allocated. Now, here's a bit of a simplification. This is a page in memory, so it's 4 kilobytes. And this is not exactly how it looks in DRAM, but you have multiple pages in the same row usually. And let's say you want to allocate some textures from WebGL. What you would do is you say you want to allocate texture of 4 kilobytes. So the operating system will try to not fragment the memory. So it will provide you with the smallest possible chunk available at that time. So we will start with the single pages. So this is isolated, so it's single. Same goes for this one. This one the same, but then you will start getting contiguous pages. For instance, these two are still considered contiguous, even though it's just 2 pages. And then after that, you will start getting the bigger chunks. So once you exhaust all the small ones, you will start going to the bigger ones, and you will get the content of this one, until at one point you get your 3 contiguous rows that you want. Now you have a part which is hammerable and a part which is not hammerable. So we need to figure out how to distinguish them. So that's the main problem now. And the answer is we can use side channels. And at the WUSEC, we're actually quite good at that. We really like them. So it was the first thing that came to our mind to try to use this one. And the side channel here is on how DRAM works. So a bit of recap. We said that when you want to read from DRAM, what you need to do is you say, let's want to read from that page. What you need to do is you activate the row, you bring it to the row buffer, and then you can read from there. And then you send it back. So the trick here is to detect contiguous memory is to touch different pages that you allocated contiguously. So you think, okay, I allocated texture 1 first and then texture 2, and you keep on going with that. You touch a different texture that you just allocated. So let's say you want to touch these first 3 textures. And this will do this process. So you take the first row and you will activate it. You read from there, and then you send it back. Second row, read it from there and send it back. And again for the last one. Now clearly, this is slow most of the time, but most importantly, it's very noisy. So you don't know where the data is going to come from. And as a consequence, you don't know what, like, the standard deviation of your signal is going to be very different depending on which pages you touch. It's very different for contiguous memory. So let's say you want to do the same, but when you have textures allocated by contiguous memory, and you want to touch again the first 3, what you need to do is you just activate that row, touch the first 3, and send it back. And this provides you with a very fast and clear signal. And you can distinguish these 2 signals from the GPU. As a consequence, you can figure out when the GPU has allocated when the kernel has allocated for the GPU contiguous memory for the textures. Now, to detect this side channel, you need timers. And turns out that WebGL provides you with 2 family of timers. The first one is based on the disjoint timer query extension. And this is very similar to clock get time, so you just ask for a timestamp and you get back the value. And this has a very high resolution. And the problem with this is that since it's extension-based, you can simply disable it. You just remove the extension, and then you resolve the problem. So to prove our theory, we found another timer as well, which is based on WebGL sync objects. And these objects are basically fences to synchronize CPU and GPU operations. And even though these are more coarse-grained, they are still good enough for our side channel. And since they are implicit in the WebGL2 standard, they cannot be simply disabled, but they need to redefine the standard, basically. And the reason why these are scary is because then you can re-implement attacks such as Spectre, for instance. So once you have these kind of timers, and you can measure, again, cached or uncached memory accesses, you can bring back to life attacks such as Spectre. So we have our 3 primitives. The next step is, what do we do with these primitives? And the answer is glitch. Glitch is our exploit that we developed, and we dubbed it glitch because of ROAMer, which is a hardware glitch, and GL because of WebGL. And the way glitch works is basically flip feng shui in JavaScript. So we call this process flip feng shui because it's very similar to any hit feng shui attack, but you do it on physical level, so in DRAM. So the first step, which is specific for our attack, is you need to allocate and detect contiguous memory. So we use our side channel. Then what you need to do is memory templating. So memory templating is the process of looking for exploitable bit flips. And basically, you just allocate a big chunk of memory, and then you start scanning for these bit flips until you find them. Then you perform memory massaging, which is the process of releasing this texture that you found with the vulnerable memory, with the vulnerable cell, and trigger the allocation of sensitive data. So what you would do is get, I don't know, any JavaScript allocation you want to compromise, and spawn the allocation of this data to have it eventually end up in the specific location in memory. And finally, exploitation, which is the act of triggering the bit flip and use like this data that you just found. So the interesting part here is the exploitation, because the rest it's very trivial to understand how it works. And the question is, what's the target of our exploitation? And the target are JavaScript arrays. So let's say you want to locate an array of 100 elements, and then you can, for instance, put an integer in there, and then a double in there, an object, so you can just create another array and place it in the same array, and a lot of other things, so other double strings, functions, Boolean, whatever you want. Now, the first question is, why would you do it? Because it's not very smart, considering that it can be very insecure to do this. But the second question is, how would you do it efficiently? Because, of course, a browser wants to keep up performances, so they need to have an efficient way to do this and not decrease the performances. And the answer is numboxing. Now, how many of you know about numboxing? Is anyone familiar with numboxing? No? Okay, well, I'm going to explain. So, numboxing, it's a consequence of the way that the IEEE consortium decided to design floating point numbers. So let's say you have these two numbers, 1.125 and 11.25. And the way this is usually stored is by using the exponential notation. So what you do is you just get the significand and the exponent. And the significand, in this case, you see is the same. So you would have 1,125 times a different exponent. So one is 10 to the power of -3, and the other one is to the power of -2. And as you can see, the significand is the same, but the exponent is different in this case. Now, in binary, what you have instead is you have your sign bit, which tells you if it's a positive or negative number. Then you have 11 bits for the exponent. And then finally, you have 52 bits for the mantissa, which is the significand. And what they designed during when they decided the standard, it was that if all the exponent bits are set to 1, and another bit inside the significand is set to 1 as well, this value would be considered as none, and none stands for not a number, which means that that value, you cannot really use it for any computation, but it's just there. So this means that you have 2 to the power of 53 minus 1 unused values in the same encoding. And clearly, smart people thought, well, what if you actually store pointers in there? So why don't we use this encoding for the browser to store pointers, and then we can use the same value to still store numbers and also objects. So the way they do it in Firefox 32 bits, so we analyzed the 32-bit version because our exploit was running on Nexus 5. But similar encoding works also on 64 bits. It's just a different formatting. So what they do is they divide the 64 bits in two parts. So you have a tag and a payload. Clearly, these are 32 bits each because it's a 32-bit environment. And what they do is they check the tag. And if the tag is less of a threshold value, which is this one in case of Firefox 32 bits, the value, the whole 64 bits, is going to be considered as a double number. Whereas if the tag is considered as if the tag is bigger than that value, the whole thing is going to be considered. No, the payload is going to be considered as a pointer. Sorry. So what happens here is that let's say you want to write in the array these two values. Well, of course you cannot write them in JavaScript, but it's just to understand what's happening. You would have like the 64 bits inside the value, and the JavaScript array would interpret the first one and the second one differently. And the first one is going to be a double, and the second one a pointer to an object. And both of them have the same payload, but the tag is different from 1 bit. Which in other terms is basically 1 bit flip away one from the other. And now you can see what's the point of our primitive. So our primitive is called type flipping. And what you can do is basically, by triggering a bit flip in the tag, you can convert any pointer into a double, which means that you can break ASLR as simple as that. And you can convert any double into a pointer, which means that you can craft any pointer without any restriction. So this gives us two primitives, an arbitrary leak with a 1 to 0 bit flip, and an arbitrary craft with a 0 to 1 bit flip. Now, someone may ask why a 0 to 1 bit flip, since bit flips are discharges of capacitors. And the reason is because of the encoding that you have in DRAM. So sometimes you have cells that are recognized as zeros, even though they're charged in DRAM. So the logical value that you see when you perform your computation is different from what is actually stored in DRAM. And that's why you can perform both of the bit flips. And then what you want to do is to get an arbitrary read-write primitive. So the idea is that you want to have an object that allows you to scan the memory and write there. So you just want to have this object that allows you to go around and scan and change whatever you want. And the way you can do this is with array buffers in JavaScript. So every time you think about arbitrary read-write primitive in JavaScript, the go-to object is an array buffer. Now, an array buffer has an header with a pointer to the data, and the data is just a byte array. And then it has a size value that tells you how big is the array. The problem with the size is that if you want to perform an access out of bounds, of course it's going to trigger an error, because you're not allowed to read that. And as a consequence, we need to go deeper. And with this, we mean that you actually need to create a fake array buffer inside the array buffer. So it's kind of an inception, and that's why the reference. And then you want to trigger, you want to create a reference to that array buffer. And the problem here is that you have two challenges. The first one is that the header of the array buffer contains other data structure that you don't know. So there are some unknown fields in there. For instance, the garbage collector root, which of course you are not supposed to know. And as a consequence, when you want to create your own fake array buffer, you also need to know this data. And the second one is that you don't know the location of the data. So you can know the location of the header, because that's the reference that you will store in your JavaScript array. So you can trigger the bit flip to leak the data and break ASLR. But you cannot know the value of the distance between the header and the byte array. So to solve the first challenge, the second challenge, we can use inline array buffers, which are array buffers that are created for values less than 96 bytes, I think, if I remember correctly. So if the size of the byte array is less than that value, the header and the data are going to be stored sequentially. And for the second challenge instead, well, then of course, like once you know the distance is like the two things, the header and the data are connected. Then once you leak the data pointer, then you can also know the offset between that and the byte array. For the other challenge instead, unknown header fields, you need something more. And this is an arbitrary read, which means that you need to first get an arbitrary read to leak that content to then get the arbitrary write. And the way we do this is by using JavaScript strings. So this class, so Unicode strings can read any value in 16 bytes. So you can read anything from 000 to FFF. And the way this class looks like is you have a flag, so it tells you what type of string you have. Then a length, which is the size of the string, and then a pointer to the string. And the first one, it's a constant. So you know that you can put whenever every kind of value, just an integer. Same for the length. And the pointer to the string is clearly the pointer to the header of the buffer, which you can leak with your type flipping primitive. As a consequence, you also have that one. So the way you would do it is you create a fake header of a string, which will point to the header of the array buffer. Then once you break ASLR, you can just reference the fake string and leak the data in there. And then you can write the fake buffer header inside your own array buffer, which you can then reference to get your arbitrary read right. So a quick recap of how this works. You have your array with the reference to the real array buffer. And you first break ASLR by triggering a bit flip in the pointer to the array buffer. Once you break ASLR, you can get your arbitrary read. So you just write your double. You create a custom double that with a bit flip will point to your fake string. And then you trigger the bit flip that will change that into a pointer, so you can reference your fake string. And then you can leak the header of the array buffer. And finally, you get the arbitrary write by triggering the bit flip again on the fake array buffer header. And then basically you can leak any data you want, and you can also overwrite any data you want. And to do this, you need 2 bit flips, 1 to 0 bit flip, and a 0 to 1 bit flip. So since you need 2 bit flips, people will ask, like, why? How is it possible that this is faster than current attacks? And the answer is because we use the GPU. So this deterministic behavior of the caches can speed up a lot the act of triggering the bit flips. So we can get more bit flips than previous JavaScript implementation, even on x86 systems. And it runs on average on less than 2 minutes. So we run it 20 times, and we tested for the average value, and it was running on average in 116 seconds. So now let's have a short demo. Yeah, so let's open this one. Let's see. Does this come this way? No, wait. Is this opening or not? Okay. So here on the left side, we have a terminal with a shell to the phone. So we cannot record the phone because you're using the GPU to trigger the bit flips. So it will conflict with the bit flips, the recording on the screen. So what we have is on the left side, a terminal to the phone, and on the right side, we're debugging Firefox remotely. And now what we do is on the left, we just check the the base address of the Firefox main libraries, which is the XUL library. And on the right side, in the meantime, we're starting to allocate the textures to look for our bit flips. So you see on the left side, we got the base address. On the other side, once we get enough textures allocated, we start looking for contiguous memory. So here we're looking for the contiguous memory. And then afterwards, once you get the contiguous memory, we start looking for bit flips. So you need to look for a 1 to 0 bit flip and a 0 to 1 bit flip. So we found 2 exploitable 1 to 0 bit flips. Now it's looking for 0 to 1. It found one, but it's not exploitable, which means it might not be in the tag. So then once it finds the exploitable bit flip, what it does is release the texture that contains these bit flips. So once you find them, you want to give back the memory to the operating system. So then once the operating system has back the memory, you can start triggering the allocation of the JavaScript objects that you want to compromise, so arrays. So then it starts allocating memory. Now it's going to show a blob of text, which I'm going to explain. So first of all, of course, you have to scan the memory for the bit flips. So once you place the arrays, you need to trigger them and locate where they're happening in the array, so you can figure out which cells are the one vulnerable. And then, as you can see here, you have the code, which is the actual exploit. So what you do is you first break ASLR, so you lick the array buffer pointer. And then, yeah, this is some bad formatting from my side. Then you create a fake string that contains that pointer, and you trigger a bit flip that references the string. And as we said, then you can create the fake array buffer. So now we have an arbitrary read-write. So what we do is lick the pointer to a function, a native function. So we just try to lick the pointer to max. And then the base of the library, it's located at a specific offset from that function, since the function is contained in there, so it's a static offset. So as you can see now, we have the same value here for the, I don't know if you can see it, let's see if I can zoom in. Can I? Yeah. So you have the same value for the base there, and the same value over here. And then eventually what I can do is read the content from there. And you will see that it's the header of an elf binary. So as you can see, you just lick the header of the elf binary, and if you want, then you can just overwrite any function pointer or whatever else you want with this primitive. And yeah, so, well, no. In conclusion, we showed that this was the first rammer exploit from JavaScript on mobile. And we showed that this was possible thanks for the GPU. So the GPU is the actual tool that provides us with the primitive that allows us to build this attack. And the takeaway message of this research is that we actually need to completely redefine the threat model. So far, everybody just look at the CPU. And of course, it's important to look at the CPU, but that's not it. And by just restraining the threat model to only the CPU, it's actually a very a very risky assumption because it means that you leave out everything else. And there is a lot more in there. So you have digital signal processor, as we said, and now on, for instance, on a server system, you also have FPGAs in the same system on chip. So you can run a lot of code on these CPUs to perform these attacks that it's much more than what is currently considered in the threat model. So basically, that's it. If you want more information, you can check on the project page of our group. And this is a QR code that brings you there. And you can check me on Twitter. I don't really tweet that much, but you can ask me questions if you have any question there. Otherwise, follow Busek. And yeah, so if you think this research is cool, you should probably join us. This is the sales pitch part of the talk. We are hiring, so feel free to ping us if you're interested in a PhD in Amsterdam.